I'll post sometime over the weekend, maybe like an estimate of what your classwork grade is thus far. By classwork, I just mean like MyLab plus quizzes plus problems plus all things non-related to the exams. We still have classes on Monday, but I don't think we'll do any new material on Monday. So today should be the last. I mean, well, yeah, we just have one more section of the book to cover. So today will be the last official class in the sense that like the last class that will cover material. On Monday, I'll just do some practice problems. Um, so, but yeah, so like if you go to the department website, you can read like the information about the exam. At least for you, like the only thing that maybe is worth mentioning is that this time every problem will be an upload problem. So just keep that in mind. So, and it's just it's basically you'll do like two uploads, like for the first, like an upload for the first part and an upload for the second part. But like it's kind of described here. And then there are like some practice problems posted on the MyLab side. The solutions for those, well, you can take the makeup, but you have to just email me about that. Then like yeah, like at some point I think the date is here, but probably early next week on Monday, like the solutions for the practice problems will be posted on the website. And then there's also like the usual summary of the sections. I mean, this is obviously like a summary of the new sections because you can use like yeah, you can use so the note sheet now it's 2 sheets. Each sheet being two-sided, meaning that it's like 4 pages. So you can put whatever you want. I mean, kind of, you know, whatever you want on the note sheets from like all the previous study guides or whatever. Yeah, it's more like maybe 60-65% on integrals. It is more tilted towards integration. Like, you know, so yeah, the ratio should be like 60-65% like integrals, and the other stuff like, you know, more about like the beginning of the semester, like the critical point, like, you know, Lagrange multipliers, critical points, curves, like arc length, things like that, like planes, intersection. That should be like over a bit like a third of the exam around that. And then yeah, I think that's more this I think probably what you need to know for now. So as I was saying, this is the last section that we need to cover for the final, which is Stokes theorem, because 16.8, which is on the divergence theorem, that's what we did last time at the end of the class. Stokes theorem kind of requires its own lecture to discuss it. So here's like the main idea about Stokes theorem. So imagine that you have like a circle, right, like this one. Then when we were trying, like say if I gave you like a vector, you know, a vector field, and you wanted to compute the work of this vector or circulate, work is also a synonym for circulation. If you wanted to compute the work or circulation of this vector along the circle, right? Well, you kind of use that on Monday's exam. Like there's Green's theorem allows you to compute the work instead of doing it directly over along this, like of computing the like integral along the circle. You can compute like a double integral, right? Which involve this combination of partial derivatives of the vector field. So like Green's theorem, what it allows you to do is like replace computation of the work of the line integral over the circle, like for example, with a double integral over the disk, right? That you see here, kind of making bounding this circle. Okay, so there's a generalization of that concept to curves that are not just on the XY plane, but rather like curves which are in space. So imagine that you take the same circle, right? I take the same circle and I tilt it a little bit. So now, strictly speaking, it's not like, say, on the XY plane. It's just like somewhere like in space, right? It's like a tilted circle. So, I mean, it kind of makes sense that you would like try to apply like some version of Green's theorem, right? Like the only difference is that you tilted it. So that's precisely what Stokes theorem says. So imagine that like this is like, there's a butterfly net. Imagine that like this is the same circle I was referring to previously. So like here you have it, okay? So I just tilted it. So what Stokes theorem says is that you can still find the work along this circle by doing like a double integral. But now the double integral just has to be any surface whose boundary is a circle. Good. So by that I mean, like, imagine of this like as the surface of like an asteroid or a planet, right? A membrane, a net, right? So if you walk, if you walk along the membrane, right, like you can walk happily without any issues, and then you keep walking, you keep walking, you keep walking, and then you hit like the circle, right? So sort of the circle is kind of like the end of the world for this membrane, right? This is where like the membrane or the net terminates or ends. So it's like the frontier or boundary, right? So what Stokes theorem says is that instead of like doing the integral directly over the boundary of this thing, you can sort of do like a double integral over the surface, which is this net, okay? And what we're going to integrate is the flux of the curl, okay? So that's why we talked about doing double integrals before over surfaces, so that we could apply it to Stokes theorem. And like the cool thing about Stokes theorem is that it says that basically you can choose any surface whose boundary is a circle. So for example, here is this net. So you could use this net as its, it is not the triple scalar product is kind of, let's see. It is a bit different. It's not quite a triple scalar product. It would just be like the ordinary, it would be like kind of the flux that we talked about last time. Yeah, this, so it's not quite the triple scalar product. In fact, we didn't, I think, even discuss the triple scalar product in the class. It's mentioned in the book, but so what Stokes theorem says is that you can choose any surface whose boundary is a circle, and you can use that to compute the work. So for example, here's a net, but you know, you can sort of deform it slightly. And now you have this new surface, and this one can also be used to compute the work. And it will give you the same answer regardless. And so I also am deforming it now again, this way, or this way, or this way. All these are different surfaces whose boundary is the same circle. And so according to Stokes theorem, you can use either any of them to find the work. So let me write that down. And that's basically the last idea of the semester. So
instead of curve independent, is this like surface independent?
Right, surface independent, provided the surfaces share the boundary, right?
Right. Okay.
So it's like, here's like, you have to think that sort of you fix the circle in space. So once you fix the circle, then you choose your favorite surface that bounds it, or whose boundary is this circle. Obviously, if you move the circle around, then like I mean, the work and all of that will be different, right? Like then you have to use again different surfaces for that new circle. But but the point is that once you have like particular curve that you care about, the answer does not depend on the surface that you use to bound it. Yeah. So,
Okay.
but yeah, like the circle needs to like I mean, I'm saying circle, but you know, it's a curve. It just needs to be a curve. It doesn't like necessarily need to be a circle. It's just that like the net is naturally like a circle, right? So yeah, the cool thing about Stokes theorem is that the answer is surface independent, provided the border, the frontier is common to all of them. Yeah. Right, exactly. The only difference with Stokes theorem is that instead of a curve on the xy plane, you allow the curve to be anywhere in space. So it's like a 3D version of Green's theorem, in the sense that you're no longer restricting the curve to be on the xy plane. Yeah. Good. And so yeah, let me draw a picture here. So again, you choose like your favorite closed surface, C. So this is like a closed surface. Sorry, a closed curve in space. And then what Stokes theorem says, like, is that you choose your favorite surface whose boundary is this curve. So let me try to draw some kind of surface whose boundary would be that curve. So I'm trying to think of it as some sort of dome, or like just like a cap for the curve. So this is like a surface whose boundary is the curve C. Okay. And so what Stokes theorem says, the content of Stokes theorem is that if you want to find the work, right? Remember this, like, what's the way in which you could write the work of F? So imagine that I just give you F's being like some vector field, some vector. So this is again like the work of F along the curve. That, according to Stokes theorem, so this is where Stokes theorem gets used. According to Stokes, I mean, Stokes was the name of a mathematician. Like they're like I don't know if you have heard of them. There's like these equations called Navier-Stokes equations on fluid dynamics, and there's like a $1 million prize about showing something about them if you want to make money in math. So there is one of the so-called millennium problems. So there are like 7 millennium problems in mathematics, each one worth $1 million. One of the 7 has already been solved, but one of the 7 is about these Navier-Stokes equations, which are sort of used to model, like, you know, like motion, like of particles, or like an airplane or things like that, like in a fluid. And here, fluid, when people talk about fluid, they just not mean like liquid. It could also be like some sort of gas. So like some sort of like the dynamics of certain things, like in a fluid. Just if you want to keep that in mind. So So it's the same Stokes of those equations. So according to Stokes theorem, what you can do instead is, if you don't want to do the integral directly, you can do a double integral over the surface. Okay. And what you integrate here is the flux of the curl. So that sounds a little bit tricky in words. So let me just write it. So here, RUV is like a parameterization of the surface. So what Stokes theorem says is that you can do a surface in like you can do an integral of the surface, and what you integrate is the flux of the curl. So this is what's known as okay. So this is essentially the last formula for the semester. So let's just do some examples to show you in practice how this gets used. Good. So and there's one more thing I have to say. I mean, just make a remark about Stokes theorem, but let me do an example first, and then I'll make that remark. So let's just. So imagine that imagine that our curve Z is the curve that connects, like this curve that you see here, consisting of the line segments connecting the point 0, 0, 1 with 1, 0, 0 with 0, 1, 0. So the curve C is the three segments connecting okay. And let's say that I gave you a vector F, which is just Z squared, Y squared, comma, X. Okay. And so let's try to find the work of F along this curve C using Stokes theorem. So find work of F along C using Stokes. So the thing is, like, without Stokes, right? What would you have to do before Stokes?
Find a parameterization of each line segment.
Right. I was going to abbreviate that by initial letters, but probably that's not a good idea. So yes, you would have to like just do 3 separate line integrals, right? And add the answers. Okay. But after Stokes, with the help of Stokes, the trade-off is that instead of doing 3 separate line integrals, you can just do a single integral which takes place on a surface, right? So the idea here is that you sort of have to find a surface whose boundary, think of it again like the boundary is sort of the border or frontier of the surface. So you have to find a surface whose boundary is precisely these 3 line segments. So can anyone think of a surface with those properties?
A triangle.
Yeah, it's almost kind of drawn like implicitly in the picture, right? Does everyone see it? So here, like the surface that we're going to use is like this part of the triangle. Sorry, and the surface is going to be just like the triangle.
And the position of it matters as well.
Well,
Well, where it is in the 3D space, it matters because if it changes, the work changes as well.
it doesn't. Okay, it doesn't matter as long as the triangle satisfies the property that it's bound, like edges coincide with these segments that I drew. So for example, like the thing is like I don't really have like a triangle, but imagine that this were like the triangle, right? And it had been like a rectangle, right? Like that we're trying to find like a surface whose boundaries are like the 4 edges of this rectangle. So if you thought of like this made of clay, you can sort of, push this rectangle with your fist and deform it a little bit. And as long as you deform it in such a way that the boundaries remain fixed, that's fine. So what I'm trying to say is
Okay.
you can, with your fingers just
makes sense.
suck a little bit, and that's okay as long as you sort of glued. Just imagine like gluing the edges of the rectangle with the edges of these 3 segments, and then like the rectangle is kind of made of clay, and then you can play around with it. So
so then how would you parameterize the surface? Would you use the equation of the triangle?
well, right. In fact, good. What happens is that this triangle is actually part of a plane. So you just, like what you have to like, you just have to find you see like you have 3 points, and there's like a plane that passes through these 3 points, and essentially the triangle is sort of like the part of the plane that's contained by inside these 3 segments. So basically what you have to do is like find the equation of the plane that contains those 3 points. So but yeah, like this is the good point of view, that you have to parameterize a triangle. But essentially, in order to parameterize a triangle, you just parameterize the plane to which it belongs. So to parameterize, you parameterize the plane to which it belongs. Okay. And I mean, this is like, you know, this is like in a sense why the exam is cumulative, because like here now there's like a question about like the beginning of the semester like inserted inside this problem, right? So how would you find the equation of a plane? You had to find the normal vector, right? And when you were given 3 points, like you could find the normal vector just by, you know, like say you have this. You have this vector, let's call these points P, Q, and R, right? So you have this vector PQ, which was like Q minus P, so that's -1, 1, 0. And you have this vector PR, which is R minus P, which was -1, 0, 1. So the normal vector to the plane would be PQ cross PR. So it's the like determinant of JK. -1, 1, 0, and then -1, 0, 1. And
Does the direction of these vectors matter?
I mean, it will not doesn't matter too much, but for finding the equation of the plane, yeah, because the normal vector will be, I mean, you know, it's only determined up to a sign, right? And in fact, up to like you can scale it also, but right, it doesn't matter too much for finding the equation of the plane. So I'm obviously choosing it strategically because I sort of know what the answer should be. So I'll like it will come out with all the positive like and coefficients being positive, but like that's not too much of a big deal. So so if you do this cross product, you get something like this. So that's a normal vector. And so the equation of the plane is just like x plus y plus z. Because remember, like you have to like the coefficients in front of x, y, z are just the coefficients of the normal vector. And then you just do the dot product between this vector and one of the points. So you'll get like x plus y plus z equals 1. Okay. If you had chosen like an opposite order, you would have had like minus x minus y minus z equals -1. At that point, it looks kind of ugly, so you probably will flip all the signs, right? Just looks better when all the coefficients are positive, if that's an option. So this is a question. This is a this is because 1 is like the dot product between 1, 1, 1, and one of the. Remember that the number on the right hand side is found as the dot product between the normal vector and one of the points on the plane. So it just comes as 1 in this case. Is that making sense so far so good? And so now you have the plane, and then you can parameterize it, and you can parameterize it like in the way in which you did on Monday, I think. So you can say, for example, that z equals 1 minus x minus y, right? And so the parameterization of the plane would be in terms of x and y is x comma y comma 1 minus x minus y. So this is like a parameterization of the plane. Is that making sense so far so good? And now once you have the parameterization, like kind of works like automatically, like you find the partial with respect to x. It's 1, 0 minus 1. Partial with respect, I mean, this like vectors should look surprisingly similar. They're kind of secretly the same ones as before. I mean, this is not like I mean, this particular case is not a coincidence, because if you remember what I mentioned last class, like this cross product does give you like a normal vector to the surface. So it's not like a coincidence that you sort of got it back again from this perspective. Okay. And so again, like by Stokes, so Stokes said, let me copy again what Stokes said. It said that the work was the integral over the surface of the curl dot this cross product. This is what Stokes said. So F in this particular case was c squared y squared x. So I don't know if you remember the formula for the curl. It's also like a Stokes theorem tends to be the longer problem on the exam, just because like there are a lot of cross product type things you have to compute if you think about it. So this is why I also did like the divergence theorem last time, because the divergence is a lot easier to compute. It's just like you sum the partial derivatives. This is like always like some sort of cross product. And if you do this curl, then you'll find what? Like you'll find 0, and then you'll find 2z minus 1, and then you'll find 0 again. So that's the curl that you get by computing the partial derivatives. So far, so good. Are there any questions up to this point? Good. You're ready now to plug everything into the. So you're ready to plug everything back into Stokes theorem. So according to Stokes, what you have to do is the integral of the curl. The curl is 0 to z minus 1 comma 0 dot product this thing. In this case, this thing gives you 111. And the parameters, like we're doing like a parameterization of the plane where the parameters are dy dx, right? So we have to give the bounds for this part, for this piece of the plane in terms of x and y. So what would be the bounds for x and y? Anyone? Again, like I think there was a similar parameterization being asked on the exam problem, I believe. So what would be the bounds for x?
Zero to 1.
Yes, there x is 0 to 1, right? And how about y? What are the bounds for y?
Also 0 to 1.
Well, that's the thing. If you said it's also 0 to 1, that's actually like parameterizing like the stuff above. It would be like a square, you know. If it's x 0 1 and y 0 1, then you're parameterizing like a square. What you can do, like what the parameterization says is that you have to look at like any point on, like, you know, the shadow of this plane is essentially this triangle, you see. So essentially you like the values for x and y are kind of contained in this triangle. So you have to find the equation of, right, what you can do if you want is like draw separately the shadow for x and y. So you get something like 1 0 0 1. And from there, it's easy to see that this is y equals 1 minus x. Because what I'm saying is that above any point on this triangle, you find like a point on the, you'll if you move your head up, you'll see like the plane, right? Is that okay? So this is from 0 to 1. So far, so good. Any other questions about the bounds or anything else? And remember that the other thing is that you cannot really have z here because z should be replaced with the formula that you found from the parameterization. So in the parameterization, we found that z equals 1 minus x minus y. So let me just replace z with that. Okay. So at the end of the day, what you're doing is the integral of 2 minus 2x minus 2y minus y. Because like that dot product is kind of easy because there's a 0 in the first and last entries, and you're taking a dot product with the y. So and that should be negative 1/6.
So that gives us the work done by that. surface,
That's what you would get
or
if
by
you,
the field.
right. If you had computed like the 3 separate works along each edge, and you add them up together, you get negative 1/6, right? So this is like the total work, kind of. You see, like it doesn't tell you individually how much of the work per each segment is, right? So like it could have been that for one of the segments is 0, and then for the other is like, I don't know, like 5/6, and the other is minus 7/6. So like it just, or minus 1. So that, like, you know, it can be like for each of the individual curves, it can be whatever it is, as long as once you add them up, you get negative 1/6. Is that okay?
Got it.
And so any questions up to this point? So it's not too, you see, like it's kind of it is a bit long because you have to parameterize this, like you have to find the surface and parameterize it, and then do all these stuff like cross products or curls, and then do the integral. But you know, this is why the surface, like if you know how to do the surface parameterization, is after that it's just like following the steps. Like the parameterization is key to many of the things that like just get done on this final exam, right? If you know how to parameterize, and after that, like the procedure is basically there's only one way to go. So the only thing that I sort of kept under the rug is this orientation convention. So let me just mention it now.
The clockwise and counterclockwise stuff.
Yeah, exactly. Essentially, like right. The idea is that if you have a curve, and there are many ways to describe this, but I'm just going to like give you like the most pragmatic way to say it. Like
Would that be dependent on the where the normal vector is pointing?
exactly. It like the way I'm going to write it is like if you walk along the curve counterclockwise, then the normal vector should point like should have like negative third positive component. So let me put it this way. So imagine that you have like your favorite curve in space, right? And I'm walking it in a certain way, but like the way I'm walking it is that if you look at the shadow curve, right? So every curve has like a shadow curve, which is like the shadow that it would make like sort of like on the XY plane, right? Like you just imagine putting like a light bulb along the z-axis and it just falls like down to. So for example, if this is like a point x comma y comma z, the shadow of this point is just x comma y comma 0, right? It just forgets about the value of the third entry. So like this is like, let me put it this way. This is the curve you care about. And this is like the shadow the curve makes on the XY plane. So the idea is that if you're walking the curve in such a way that, so the convention is that if you are walking counterclockwise, and by counterclockwise, I just mean that it's sort of counterclockwise on the shadow, right? If you see like the point moving, that's like it looks like counterclockwise on the shadow curve. So if you're moving counterclockwise on the curve, then the normal vector to the surface should have like positive third entry. So it should be something like this.
So it's the right-hand rule, essentially.
Yes, it is a kind of different way of writing the right-hand rule without using the word right-hand rule. But yeah, there's like a way to do this with like a literal, like, you know, right-hand kind of thing. Yeah, yeah. So yeah, but it's all it's all like a different, like a secret version of the right-hand rule. The thing is, like, you know, like right-hand rule can be like stated in many different ways. Like it may be explained slightly different on the book. They're just like all equivalent to one another. Then the normal vector to the surface.
That's why I was asking earlier about the normal vector when we were finding the plane, because I thought, what if the direction of work will be dependent on it?
Right. So right, like what I was saying, like back to your question is that for like, you know, for finding the actual equation of the plane, that does not matter, right? But right, once you parameterize, correct, like if this cross product had come out as -1, -1, -1, for example, right, that means that you should, like, you know, change the order of the cross product, because like this curve is kind of being walked counterclockwise, right? If you look at the shadow of this curve of these like 3 segments, they're being right. So once you take the dot product, you do have to check that the normal vector had like positive third entry, but not at the moment where you're just trying to find the equation of the plane, right? For finding the equation of the plane, that doesn't really, it's kind of insensitive to it. But yeah, the point, what I like, you know, hit from this example was that we actually secretly wanted like the one that had like third positive component, but the explanation is because of this fact. Yeah. Good. Any other questions? So let's do a mega example where like we'll do find everything, and so you'll see that like a big example. Okay, so let's start with something innocent. And by that, I just mean that I give you like the circle of radius 2 on the XY plane. So unfortunately, this one is kind of difficult to draw. I mean, because I'm trying to make it like with 3D perspective. So, but this is just x squared plus y squared equals 4. So this is really like a circle on the XY plane. Like maybe, let me see if I can draw it like a bit different. Maybe that helps. Okay. And I gave you this vector. Okay, and so let's try to find the work of f along this curve, along the circle. And we'll do it in 3 different ways so that you see that they'll all agree. So let's try to find the work. Okay, so the first way in which we're going to find the work is just using the actual line integral, like doing the actual definition of work. So doing it first like with the directly, like so the first method would be directly as a line integral. So by that I just mean f dot dr, which remember that was the same as f dot v dt. So let's try to do this. And so in order to do this, you have to parameterize this circle, right? So what's a parametrization of the circle of radius 2 on the XY plane?
Two sine theta, two cosine theta.
Yes. I mean, it's better to write it 2 cosine 2 sine because that
Yeah,
way
yeah.
it moves counterclockwise, right? But yeah, it's correct. And then this may seem a little bit gratuitous, but I'll put like, because we're thinking of it like being like drawn in 3 space, like I'll put like a 0 for the third entry. That doesn't really make a lot of difference in the calculation, whether you included this or not, but it's more convenient to put the 0 there. Okay, and so f becomes along this circle. Again, this was the definition of f, but with this parametrization, y is 2 sine of t, right? Z equals 0, right? Because like we are looking at it on the circle, and x squared becomes what? 4 cosine square of t, right? So the dot product that we're doing is the integral from 0 to 2 pi of 2 sine of t comma 0 for cosine square of t dot the velocity vector, which is negative 2 sine of t 2 cosine of t comma 0 ct.
And the velocity vector we got by taking derivatives.
Yeah, it's just the derivative of this position vector
Yeah.
of the circle.
Mhm.
And so this is a easy dot product because the second entry is 0 here and the third entry is 0 here. So only the first entry contributes anything. So you get 0 to 2 pi of minus 4 sine square of t dt. And well, here you should probably have on your note sheets or whatever in case it's needed, like there's like there's like an identity for what sine square is. It's like 1 minus cosine of 2t over 2, something like that. But there's like a way to integrate that. I integrate that with that identity, and if you do that, like you'll find like negative 4 pi. Is that okay? So far, so good. Any questions about this? So
So does that mean that we could have also done just pi r squared technically?
well, when you say pi r squared,
Because when we're doing the double integral, right, for Green's theorem, aren't we
Right,
just finding that?
right, in this, correct, like, if you're doing, like, I mean, if you're being asked to find it directly as a line integral, this is what you're supposed to do. But right, like the second way I was going to do it is by doing like Stokes theorem, right? Which secretly will be like Green's theorem. It's just that now I'm going to call it Stokes for the moment. But yeah, like, we can, like, this pi r square will kind of come from the next point of view. Yeah, but not like, you don't see it directly here because here we're not doing the double integral yet, right? But so this is like,
But also this looks like it's the area of a circle with radius too.
well, right, but I mean, yes, but that has to come from the calculation. Like, do you have to see that like from the curl? Because like in Green's theorem, you have to compute this difference of partial derivatives, right? So what you need there, let's like write it down, but you'll see that it's not like it is more like of let's see. Yeah, it's more like for the because of the particular features
Oh, that
of
makes sense.
F,
Yep.
right? Yeah. So now I'm going to apply Stokes, right? Like I'm going to use Stokes. So here you have again the circle of radius 2. And what Stokes says is choose your favorite surface in the world whose curve boundary is that curve, right? And so the most obvious surface that you might see there is like the disk, right? The flat disk on the XY plane. Everyone, like, again, it's kind of like looks a bit weird just because I'm trying to draw this like all with the 3D perspective in mind, but just think of with the disk on the XY plane as the surface, right? So like essentially what I'm doing here is like Green's theorem, but I'm not calling it Green's theorem because now I'm seeing it just like as a special case of Stokes. But essentially, yeah, I'm going to compute it almost as you would have computed this with Green's theorem. So, but I'm trying to do it like as a Stokes theorem problem, so that you see like the logic here. So. So in this case, you have to parameterize the surface, right? So here we have to parameterize the disk. What's the useful parameterization for the disk that you could use?
The same one we did in the last integral, polar.
It is kind of the same, but like the previous one was just for the circle, right? It is with a polar, right? It's just that now the radius is not necessarily 2, right? But it's basically besides that, there's it's kind of the same parameterization. So it's like you can parameterize the disk as r cosine of theta, r sine of theta, and then 0, right? And remember, because it's a disk, it's like a surface, so it needs 2 parameters, right? So that's why you need 2 variables here. The thing to be aware of is that the theta goes then from 0 to 2 pi, right? And then the r, because it's a disk of radius 2, r would go from 0 to 2. Is that making sense? So let me put it this way. I'll write it this way because it would be more useful to emphasize this point about the orientations. So if you call the parameters theta and r, you will find first like the derivative with respect to theta, and you get minus r sine of theta, r cosine of theta, and then 0. And then if you do the derivative with respect to r, you get cosine of theta, sine of theta, and then 0. And so when you do their cross product, you get determinant of ijk of minus r sine of theta, r cosine of theta 0, and then cosine of theta, sine of theta 0. And this gives you what? It gives you 0, gives you 0. And this one gives you minus r sine square of theta, minus r cosine square of theta. And so this one gives you 0, 0, negative r. Okay. So you see, if you did the only reason why I'm doing it here this way is that if you do the cross product in this order, right, then the normal vector, remember, like secretly, this is like a normal vector, right? The normal vector is coming out with the third entry being negative. And due to our conventions, since we're moving counterclockwise here, we needed the opposite order for the cross product so that the conventions like are correct. So because of like, I'll write it down. So this is negative third entry. So we have to use the same cross product, but in the reverse order. So due to the conventions. Is that making sense? So that's the only thing that one needs to keep in mind here. So again, Stokes said that the work equals this dot product between the curl, and this is how I'm going to write it here. So what we haven't found yet is the curl. So if f is y to z x squared, the curl again, this is how you would find it. With this thing about the partial derivatives.
Do we first find the curl and then parameterize it, or?
Right, you always find it first in terms of x, y, and z, correct? Yes. So the curl itself is found in terms of x, y, and z, and then you rewrite it in terms of r. Like for example, in this case, you rewrite it then in terms of r and theta. That's a good question, actually. In fact, I mean, there's actually like a way to compute it directly from r and theta, but we don't do those things here. So so this is what you get in terms of x and y and z. It's just that in this context, right, it becomes -2 r cosine of theta, and then -1 because you use the parameterization. But yeah, like the curl is always found first. Let me write that down. You find it first in terms of x, y, and z, and then you rewrite them in terms of the parameters. So find it first in terms of x, y, and z, and then rewrite in terms of the parameters. Okay, so with all of this in place, what we're doing is the integral from 0 to 2 pi, from 0 to 2 of the curl. The curl is -2 r cosine of theta, and then -1, and then the cross product in this case was 0, 0, r, dr d theta, right? And that just gives you 0 to 2 pi, 0 to 2, which is, and then this cross dot product is just negative r dr d theta. So really, this is secretly, yeah, like the stuff about the area, because r dr d theta is just like the area in polar coordinates. And so you just find minus 4 pi, which is, yes, it has to be the same answer because, right. Like that's exactly, yes, yeah. Is this okay? Is that making sense? Any questions, other questions? So far, so good. Any other?
So what's the third way you were going to calculate?
Right, good. So the third way is just to emphasize this point that you can really choose any surface that you want. So like right now, the surface that I chose was the disk. Let me pull it up. And now I'm going to use like this salad bowl as my surface. So we're going to do again the calculation, but with this different surface as our choice. So I'll do it with an inverted paraboloid kind of. Just to this, like exactly this is what you would have found if you had done Green's theorem. It's just that I rewrote it as a Stokes theorem computation, but the last third way is authentically new because like the surface is no longer on the XY plane. So the last one is like actually something new, but it's sort of just to show you that it's like it is going to give you the same answer. So the third way is Stokes again, but with a different surface. So Stokes, obviously, you know, the whole point of Stokes theorem is just to choose one surface. So this is just mostly to show you that if you had made a different choice, then that still gives you the same answer. So option 3. Stokes with a different surface. Actually, it won't be in this case. In the one that I'm about to do. Yeah. The cross product will be more interesting in this one. Because you'll see, let me draw the picture first. Like my idea right now is to use, like, you have the disk. Sorry, you have the circle, but now I'm going to use this salad bowl, right? I don't know if everyone can see it. And you see, like, the cross product should give you like the normal vector to the salad bowl, but now the normal vector is kind of like this, right? So it will have like entries, like not just like on the third component, it will have in the first and second components as well. So now the surface is just going to be this inverted salad bowl, or this parabola.
Is it practical to just like choose a different surface that is a paraboloid? Like, isn't it just easier to find a surface that's just flat?
Well, if you can find, right. In this example, obviously, like the disk was
Just for demonstration.
Right. In this case, this is the optimal choice, but on Monday I'll do other examples about Stokes where it's just like, you know, just because like the curve is no longer on the XY plane, that you cannot really find like the flat example, right? But yeah, like the point also here is like to show you that, you know, just because you can use different surfaces doesn't mean that they're all equally efficient, right? So but it's just to, like, you know, practice a little bit like how to do these problems. But yeah, good. Yeah, that's the idea, correct. So just notice that in this case, if you write it in terms of polar, like z becomes 4 minus r squared, right? So that's another way to think about this parameterization. And so like the parameterization that we're going to use now for this paraboloid. So this is like the parameterization of the paraboloid. So notice that the difference between like the parameterization of the disk and the paraboloid is that for the disk, this was 0. So essentially what you're doing is like, imagine like just like you took the disk, like the third entry of the disk, and you with your finger start pushing it up at different heights. So that's how you get like the third entry now to be non-zero. But like the values for the parameters are still essentially the same, because theta still goes from 0 to 2 pi and r still goes from 0 to 2. Okay. And again, just by analogy with the previous case, like we noticed in the previous case that the correct order happened to be first with the partial derivative with respect to r. So let's do it in this order just to see if we find like the convention that we care about. So when you do the partial derivative with respect to r, you get cosine of theta, sine of theta, and then minus 2r. And when you do it with respect to theta, you get negative r sine of theta, r cosine of theta, and then 0. And so they're cross products. If you compute it, you'll find something like this. So you see, this is an example where the first two entries are non-zero. And so here, the important thing is that this, like the important thing here is that the sign was positive. So important that sign was positive. Okay. And then the curl had been, remember, the curl had been -2, oops, sorry, -2, -2x, -1. So it's still the same, written in the same way as before. So now we're doing the dot product, but we're doing just like a dot product of different things. So 0 to 2 pi, 0 to 2 of -2, -2r cosine theta, -1 with 2r squared cosine of theta, 2r squared sine of theta, and then r dr d theta. Okay. And this will be the integral from 0 to 2 pi, 0 to 2 of, if you do the dot product and simplify it a little bit, you get -4r squared cosine of theta, and then -4r cubed cosine of theta sine of theta, minus r dr theta. Okay, and the point is that really when you do the integral in theta, you know, like the integral of theta of cosine from 0 to 2 pi is 0, and this also from 0 to 2 pi gives you 0, and so that's why these two terms actually cancel. I mean, give you 0, and the only thing that survives is -r, but that then brings you back to the same integral that we had before. So this one gives you 0. This integrates to 0. And then also this one integrates to 0. And so you end up with like the integral from 0 to 2 pi, 0 to 2 of negative r dr d theta. And so price that's just like negative 4 pi. Is that okay? So it is an example where you know it was a different surface. It was a little bit more tedious, right? But it shows you that it gives you like it's sort of consistent, right? Like it gives you the correct answer again.
Question.
Yeah.
Would this concept still work if the surface, say, was bigger past that boundary? Like, so it ends at that circle, but then in the
Yeah,
z
sure.
direction,
I get
if
what
it
you're
bleeds
saying.
out.
Right. There's like this option for a 3-point version, right? For like which we won't do. But yes, good point. Like if you had like right, it is really a liberal concept, like in the sense that you just do whatever you want as long as it's the same surface. I mean, as long as the boundary is the same. So it is like, let me.
So you're saying that the surface could extend to positive infinity on all directions, and it will still be the same.
Yes, here it is. You see the surface?
That's pretty crazy.
Yeah, I mean, I could even like, you know, you can even like do more crazy thing. Like, you know, you can, it's really like, think of it as some elastic material, right? As long as you sort of like sew the, you know, the boundary to this circle, then you can just push it with your, like, you know, it's like one of the scary movies where like someone grabs you in a bag and you're trying to escape, and then you just start pushing with your like fists everywhere, like, and then you just get something crazy. So this is like, yeah, it is like, God knows how to parameterize the surface, right? I'm not saying you could, because like it's just like a random picture, right? But it will give you it would give you the same answer. The integral of the curl, if you did the integral of the flux of the curl over this surface, it will still give you negative 4 pi.
So I have a question. Would this math be used like calculate something related to a venturi in physics?
To the what?
To a venturi in physics, where like
well, I just didn't hear like the last word before physics. To the what?
a venturi, like basically a rocket nozzle where like the velocity of air going in, and then it compresses and it speeds up.
I see. Yes, it's probably like what I was going to mention. In fact, this like, since this was the last example I wanted to do for now, let me. Yeah, it's probably, sorry, just to let's go here. Yeah, I'm pretty sure like that could that's one way if you could use it. Like the most like famous way in which this can be used, like again, it's like for like finding like Maxwell's equations of electromagnetism. So let me see which one it will. Okay, right. Yeah. For example, like they're like therefore, I think I can mention this before. Like there are 4 equations of Maxwell for electromagnetism. Well, like there are like 2 ways in which they can be written down. One is like in terms of like integrals for the electric and magnetic field, which is like the integral version. The other one is like the differential version, which is just like about like certain conditions on what the partial derivatives of the electric and magnetic field satisfy. So for example, if you like, maybe this is a little bit easier to understand. If you look at the differential equation, like one of the Maxwell's equations tells you that the divergence, which you already talked about, that the divergence of the electric field is basically 4 pi the electric charge density. So for example, this tells you that if you have something positively charged, the divergence is positive. And if you have something negatively charged, the divergence is negative. So that tells you, like, for example, that a proton, which is positively charged, produces an electric field with positive divergence. And so if you have seen like the pictures for like the electric field of a proton, that's why they're drawn with like as a source where like there's like radial lines emanating from the proton away from it. But like for an electron, you draw the electric field lines towards the electron because the divergence is negative. So remember, the divergence has to do with this thing of whether there's like, maybe I didn't say it explicitly, but the divergence is related to the flux. So it is, of the flux of the electric field is sort of telling you that like protons and electrons produce like electric field. And then like one of the other equations of Maxwell is that the magnetic field has no divergence. This is called like a solenoidal vector field. And that just tells you that there's like no analog of protons and electrons for magnetic fields. That's like what physicists call like there are no magnetic monopoles. And like one way to say that heuristically is like, for example, when you take a magnet, you know, magnets have north and south poles, but when you cut a magnet into two, like interestingly enough, you get two new magnets, right? You don't cut a magnet and isolate the north pole and isolate the south pole. It sort of come kind of in pairs. So in fact, like they're very, essentially people are very interested in finding magnetic monopoles. If you could, like you probably get a Nobel Prize. But at this point, like the idea is like there are like no analogs of protons and electrons for magnetic fields. And then the last two equations of Maxwell involve the curl of electric field and magnetic field. But you know, the way in which you actually can get to these four equations is like if you start with these like integral versions, and then you apply like these theorems that we saw. So for example, let me see. Oh yeah, here it is. Like there's like this is like saying that the work kind of, or the circulation of the magnetic field, right, is like the integral of the curl. And this is just Stokes theorem, right? So you start playing with the theorems like that we just discussed, and that's how you end up getting to like the four versions of Maxwell's equations. But yeah, like, you know, as I said, like there's also this Navier-Stokes equations, which probably is more related to what you were asking me about the rocket or whatever. But yeah, so there's like a Navier-Stokes equation that involves like the divergence and oh yeah. Well, I mean, yeah, it's just Wikipedia is kind of useful, except for certain articles, but this is a longer story. So yeah, like for fluid dynamics and things like that, there's also like divergence and curl and other things appear. And then finally, maybe just to wrap this up, there's like the millennium problems that I was telling you about. So there's like 7 problems, each one worth $1 million.
Have you ever attempted any of them?
Sorry?
Have you ever attempted any of these problems?
Who? Me? Oh, no, people have attempted them, but people who are smarter than me. I mean, like this one is the only one that has been proven. And also people don't openly say that they're working on them, you know. It's like saying like if it works, then you say it, but like it's kind of something to work on your like in a dark room, so that you don't tell people anything that they think you're crazy for trying to attempt them. But like this is like the only one that has been proven. I actually did like I did like one of these Barn seminars about this Poincaré conjecture. It's on the YouTube channel if anyone wants to watch it. And then there's some of you might be interested in this one. This is about computability and algorithms, kind of like if every problem, which is something about like how efficiently you can solve certain things in computer science. And this is the one about the Navier-Stokes equation. So you can you should read it, like you can check it out. They're all like very important problems. That's why each one is like it would be like bigger than a Nobel Prize. Like not mathematics does not have like a Nobel Prize. There's something called the Fields Medal. But like even like it would be superior to a Fields Medal. Like I mean, this would give you a Fields Medal probably, but I mean, it's beyond that. So it's millennium problem, right? So in principle, you have to wait until year 3000 to find new problems, unless humanity is gone by then. But I'll see you, yeah, on Monday. But this is kind of the last topic for this course. So on Monday, we will just do examples probably about Stokes and divergence, because those are like really the last, like the big theorems that we have to deal with for the final. So I'll see you on Monday. If that sounds good.
All right. Have a good one, Professor.
Okay.